Query blocks are units of optimization, and we're going to break an SQL query into its multiple query blocks, optimizing one block at a time. So the example you see on the bottom of the slide here has an outer query block and a nested query block. Because the optimizer only sees one block of the query at a time, it doesn't do a global optimization in some sense of the whole query. So an important goal is to try to flatten these query blocks into a single query block when possible before giving it to the optimizer. And there are query optimizations often expressed as query rewrites that can do this. And so that's an important area of optimization we will not cover in this class. In this class, we'll just assume we have our query blocks. They've been given to us, and we have to optimize them one at a time. But you should be aware that there are techniques to flatten them in some cases. Uncorrelated nested query blocks. Those, remember, are nested query blocks that don't have any reference to the aliases or the tables of the outer block. If your nested block is uncorrelated, you only have to run it once. And so its query plan is just a query plan for doing just that particular subquery at once, and then you can store its output in a materialization operator for use in the outer query block. If you have a correlated nested query block, then you're going to have to evaluate it once per tuple of the outer query block, and that can be quite expensive. Now, again, rewriting can help us sometimes. Sometimes you can decorrelate a correlated subquery and then flatten that and turn it into a bunch of joins that the optimizer can treat as one big query block. Query decorrelation is beyond the scope of this class. It's kind of a cool topic, but a bit esoteric, so we won't go through it here. All right, another thing to note. Within a block, the plans that we're going to look at are all the relevant access methods for the base tables for each relation in the from clause, and then all left deep join trees. These are join trees where the right branch is a base table, and so you see that in the upper right here. That's a left deep query plan. So we're going to look at all of these left deep join trees, and we're going to consider all the join orders and all the join methods that we could do in a left deep fashion. And that's the SystemR optimization space. In our examples we're going to discuss today, we're going to have our familiar schema of sailors and reservations for boats. So the reserves table has tuples that are 40 bytes long. We have 100 tuples per page. We have 1,000 pages. And we have 100 distinct boat IDs. For the sailors table, each tuple is 50 bytes long. We have 80 tuples per page. We have 500 pages full of tuples. We have 10 distinct values for ratings, and we have 40,000 distinct sailor IDs, one for each row. All right, let's focus first on physical properties of query plans. There are two common physical properties of the output of a query plan. We have never talked about physical properties of outputs, but there actually are two possible properties that come out of our algorithms. One is that the output is sorted. There might be a particular order on the output. That's a physical property of the output in the sense that the relational algebra doesn't capture sort orders. So it is sort of a physical property of the implementation that it produces things in a sort order. Another possible physical property is the output is coming out hashed in the sense that all matches are together, and then once you see all the matches and you move on to a new value, you'll never see those values again. So the results essentially of hash joins or of the hashing algorithms we've seen earlier in this class. So those are examples of common physical properties. Some operators produce these properties as part of their output. So index scans, for example, will produce the output sorted by the index keys if it's a B+ tree. Sorting will produce its output in the sort order specified. Hashing will produce the output hashed in the grouping specified, right? And then certain operators, like merge join, require these physical properties on their inputs. So if you're going to do a merge join, the two sides that you're merging both have to be sorted. If they're not sorted, you sort them as part of the join algorithm. But if they are sorted, you don't sort them as part of the join algorithm. So in some sense, merge join is asking for its two inputs to be sorted one way or another, either because they were sorted by operators below or because they are sorted explicitly using a sort operator. But you can think of merge join as requiring the property that its inputs are sorted. And then certain operators preserve these properties and pass them along. So for example, merge join preserves the sort order of its inputs. If the input to the left-hand side of merge join is sorted, the output of the merge join will be sorted the same way. All right? Nested loops join, interestingly, preserves the sort order of the outer relation. So if the outer relation to a nested loops join is sorted, then the tuples coming out of the nested loops join will be sorted in the same way.